Oh, well, thanks, John. So I hope I can live up to that introduction. Yeah, exactly. So looking at the other speakers you've had in the seminar series, I hope this won't be too much of a jolt or a change of pace. I'm not going to talk about policy or technology forecasts, and I don't think I'm even qualified to do that.
But I play a couple times. You let us know from your current posting.
Oh, okay, good.
I think the audience generally likes it.
Okay, good. Well, anyway, I'm going to try to tell you about the science of batteries, and I guess you can decide what that means for the future of battery technologies. And I'd like to emphasize the physics of next-generation batteries. So it's somewhat summarized in this slide here, where if you open up a battery, for example, a lithium-ion battery, but even more generally, we'll talk about other types of batteries today as well, then your basic setup is sketched on the left here, is that you have an anode and a cathode, which are the electrodes, which basically liberate electrons that go through the outer circuit as ions generated by Faraday reactions are shuttled through the separator to the other side. And that's sort of what the battery looks like at the sort of macroscopic engineering scale. If you zoom all the way down to the smallest scale, then you're really at the atomic scale of the material itself. And there's been a lot of wonderful work in material science and chemistry in developing new battery materials that have, for example, high energy density or good transport properties. And so I would say sort of this is the chemistry scale or the materials scale. This is the engineering scale, both very important. But what I'd like to focus on today, though, is sort of in between here, which is sort of the mesoscale, which is there's actually a whole bunch of length scales between the atomic and the macroscopic, which have a lot to do with how the battery actually works. And if you want to optimize and understand and develop new batteries, you also have to think about these middle scales. One sort of motivation for why this is interesting science could come perhaps from Bob Laughlin's article in 1999. He's a professor here in physics, you may know, called The Middle Way, where he argues that some of the most interesting science of the next century will in fact be somehow in the middle. It's going to be mesoscopic length scales and phenomena that occur in between the atomistic and the macroscopic. So I'll give you a few examples of that theme. The first will be to look at phase separation phenomena in lithium-ion batteries. So the motivation for this work and the main application that I've worked on in this topic is the material lithium iron phosphate. So this material was first proposed for lithium-ion batteries and studied by John Goodenough at Texas and published in 1997. And a quote from the last paragraph of that paper is right here. This material is very good for low power applications. And they speculate that the reason that perhaps you cannot achieve higher power has to do with the movement of a two-phase interface. So they recognize already that this material undergoes a phase transformation, which they believed would limit its performance. And so how did they know that? Well, one easy way to see it, it has a very wide voltage plateau. So if you look at voltage versus state of charge, so this is X in lithium, X iron phosphate. So from 0 to 1, you're essentially filling the cathode with lithium, and you have a very flat plateau. Now that's generally a good thing for battery operation. It also means that you have a phase transformation going from an end-member state here at low concentration to another one at high concentration, which are both stable phases. And the reason it's so flat is that you're just moving a phase boundary and converting one phase into the other, so it's always a constant chemical potential and hence constant voltage. So material scientists, when they see this sort of thing, of course, they know that that means there's phase separation going on, and they speculated that microscopically the way it happens is there's a particle of this lithium iron phosphate material, and as you're inserting lithium or removing lithium, the interface follows a sort of shrinking core picture where one phase replaces the other. And then that thinking was encoded in the standard battery modeling software that's actually still used today pretty widely in industry, developed by John Newman and collaborators, which is that they have basically particles that represent different regions of the electrode where you imagine this sort of shrinking core phenomenon is occurring. A very reasonable starting point to study this material. But it turns out that the reality is a bit more complicated, and this is where I actually first started to get involved in battery research based on the motivation of this problem. So first of all, in addition to the science getting very interesting, also sort of from a technological point of view, it's a pretty interesting story because only a few years after it was called a low power material, it actually became the material of choice for high rate lithium batteries. It was really kind of a game changer, actually. In fact, by 2009, there's a paper that called it ultra-fast and demonstrated, in fact, that you could discharge the material in 9 seconds. Okay, so it's clearly very high rate capability. I remember actually in the old days, in the 90s, we had power screwdrivers, but we didn't have power drills because we did not have a good enough battery. And then those batteries, lithium iron phosphate, allowed us to have power drills and then all kinds of other applications that we're seeing today in terms of vehicles and other applications. So what happened? Well, let's see. One thing that happened is that we went from the original experiments involving micron scale particles to really small particles, nanoscale particles. So here you see, for example, 80 nanometers or even 20 nanometer size particles really approaching the single crystal limit. And also atomistic calculations showed us already in 2004 by Cedars group that this material actually has very high intrinsic rate capability for solid diffusion. And it's also a very anisotropic material. It has sort of a one-dimensional diffusion path, which if you had a perfect crystal is fast. So one thing that's nice is if you shrink the battery down, you are able to access somehow the pure material properties of the system. But I'll argue for you that I think there's actually more going on when you go to the nanoscale. And that's related to this phase separation concept. Now, what really got me into this was actually this paper right here, in fact, because this was one of the first papers that actually visualized phase boundaries in lithium iron phosphate. And so if you look at this picture here, that's a 200 nanometer scale bar. First thing you notice are these sort of stripes along the surface, which are in fact, and they can identify as different phases of either the high or low density phase of lithium iron phosphate or iron phosphate. Well, first of all, it can't be a shrinking core because you can see the phase boundaries. They come right to the surface. Also, it's highly anisotropic because they're sort of straight aligned with a certain crystal axis. Later papers show that there are different crystal planes that tend to align the phase boundary, so it doesn't always look like this. So clearly it's a complicated problem. And this then became a major focus of my research. I'm going to spare you the mathematical details. So this actually is work that really was a major focus for me in mathematical modeling of batteries, but also led to a general theory of modeling chemical systems undergoing phase transformations coupled to chemistry. Okay, so if you're interested, I can show you a little bit of that maybe in the questions, but I won't get to it now. What I'll just show you now is what are the predictions of this theory in this situation here. And one of the interesting predictions right away was that phase separation is a rate-dependent phenomena and in fact can be suppressed at high rates in nanoparticles. So I'll show you this here with a sequence of movies here of simulations. So first of all, one interesting feature of this theory is that unlike previous work on phase field modeling, that there's a long history of modeling phase transformations, we're able to connect phase transformation behavior, as I'll show you here on the left, with the voltage profile. This is voltage versus composition on the left. So you can see how the microscopic details of phase separation connect to the voltage. So first I'll show you what happens at a low rate. So if you had a low rate, then basically the voltage kind of actually overshoots the plateau. And how far it overshoots, I don't know why that's not playing. Oh, come on. I've never had these movies not play before. Okay, there we go. Okay. Anyway, thank God. All right. So what happened? You see, it overshot the plateau. It got to this point here, which actually is an unstable point, and then it phase separated into sort of high and low density phases. And I have no idea why my movies are not playing. I wonder if maybe I took this out, if that would help. Okay, so here we go. Anyway, so now you see actually microscopically how the phase separation process connects to the plateau. You literally see the two phases I told you about, one replacing the other. And of course, some other things are going on as well, but more or less you're following that voltage plateau with a phase separated system where you're basically replacing one phase with the other. So imagine that profile you're seeing is kind of looking down on the crystal, like those stripes I showed you, and we're sort of nucleating a stripe of one phase, which is then kind of crossing the system to get to the other side. Now, the interesting prediction of this theory is captured here. This is actually an analytical, mathematical prediction of this theory done by linear stability analysis, which is that it's basically taking, imagine a movie like that where you have a system that's filling homogeneously and you ask, if I put in an infinitesimal perturbation, will that perturbation grow or not? In other words, is it stable to perturbations? And so the example I just showed you there, of course, is not stable. And that's the case when you're at low current. That was this situation where you enter the two-phase region, it's unstable, and then you leave it. But if we go to a little bit higher rate, which is the situation B here, we enter the unstable region. It is actually unstable there, so you're starting to see perturbations grow, and then you leave the unstable region, they flatten again. And so you notice it actually did not quite manage to phase separate. And interestingly, this theory predicts that there's actually a critical current above which, as long as you hold that current, the system will not phase separate. So that's shown here. And so that's, by the way, not numerical error. That fuzziness there is actually, we're putting noise in the simulation to try to trigger phase separation phenomena, but they're not happening because the system is stable. But interestingly, it's still in equilibrium a phase separating system. So if I go, let's say, to 50% filling at the high rate and then I turn off the current, you're going to see it phase separate. And I'll show you that on the next slide. So basically, the fact that you're holding the current actually stabilizes this so-called solid solution and prevents phase separation. And that allows you to have higher rate because you have a larger active area, and it puts less strain on the material and allows it to cycle better. So basically, and this is a feature that we predict would happen in nanoparticles. Now that was a very simple 1D model of the system. Here's a little bit more sophisticated model. So in order to get the details right for this material, you need to add a little bit more physics. So one important thing when you're dealing with solids is elastic stress. So if you imagine you have a crystal and you're inserting lithium, the lithium wants to basically change the lattice constant of the crystal. So typically it'll expand. What's a little bit strange about lithium iron phosphate is it expands in two directions and contracts in the third. So it's kind of a complex elastic response. And what that does for you is it actually creates these tilted phase boundaries I'm showing here. So the one nice thing about this work also is that we were able to make use of material properties that were calculated using quantum first principles calculations by Professor Sater at MIT. So the movies I'm showing you involve a model that actually has no fitting parameters, essentially. We just take it straight from those simulations. And so as I showed you before, if I go back again to this slide, imagine I went to 50%, it's homogeneous, and then I let it go. You're going to see it drop down into the phase separation region, but now we'll see it happen with elastic coherency strain. And so there you see the instability. And it forms these stripes, which want to be at a certain angle. And anyway, and that's actually reminiscent. In fact, it's the same orientations observed in this particular study. And if you look really closely at the study, you can also see it's a perfect crystal. So it's a so-called coherent phase boundary. So there are two different solid phases, each with a different lattice constant. But they kind of mesh together in a very smooth way like this. So that's called a coherent phase boundary. Okay? But then you might say, what about these stripes here? Well, what we found is that if we turn off the coherency in the c-axis here, which is this particular orientation, then we actually do get the stripes. So you see it wants to make those diagonal stripes, but it turns out when you get rid of that coherency strain that it actually slightly prefers to be tilted the other way. And sure enough, if you read this paper carefully, actually they do mention observing micro cracks along the direction of these stripes, again confirming the theoretical interpretation and prediction that elastic stresses are responsible for these stripe patterns. And then also we can revisit the simulations on the last slide involving suppression phase separation, now with elastic strain in a more complicated simulation, and the same story exists. So here we are filling the material with lithium at a slow rate, and so you see it phase separated, it formed these phase boundaries, and eventually you go from being empty to being full. But if you go at a somewhat higher rate, then you see that what we call quasi-solid solution, where the material is trying to phase separate but can't quite do it. And if you went any faster, the movie would be really boring because you would just see it homogeneously turning from black to white because the phase separation is completely suppressed. And elastic stress, by the way, enhances that effect of suppression because if you phase separate, you suddenly create two different solids with different lattice constants, and that costs energy. The system actually doesn't want to do that. Okay. So there's a lot more to say here, but these kind of summarize the theoretical work that I did. If you notice, the year of the paper is 2012. That was basically when this work was done. And then a number of years later, there's been some very beautiful experimental work right here at Stanford. And it's in fact the reason that I'm here on sabbatical this year to work with Professor William Chu, who's in the audience here. And his group has done some very beautiful imaging experiments on this material and others in situ during battery operation. And there's a number of different techniques that they've used. What I'll just focus on is some recent results from a paper that we've recently submitted, where there's basically a microfluidic liquid cell with a transparent electrode, and you have individual lithium iron phosphate nanoparticles sitting on the electrode, and you can literally see them as they're transforming using also X-ray methods, so you can detect where is the lithium basically. So these color images are telling you where the lithium is. So basically, as here you can see, for example, this 0.6 C it just refers to the rate. So this is a little bit longer than 1 hour of inserting lithium into the particle. So you can see you're forming some sort of structure there. This is the delithiation, removal of lithium. And already you can see here that there is evidence, pretty strong evidence in these experiments, consistent with the theory that we have suppression of phase separation. If we go to a higher rate, notice it looks pretty homogeneous. Also, if you take one of these homogeneous particles and you turn off the applied current, you set the current to 0, you hold it at open circuit, then it relaxes into these kind of structures. And I'll just remind you, the movie you just saw had some stripes looking like this. This is actually a simulation of a finite-sized particle with this crystal shape. And they look pretty similar. And again, keep in mind the theory is 2012 and the experiments are 2016. So it's, I guess, a nice verification that we're able to use these continuum mathematical models to connect quantum predicted first principles material properties and macroscopic behavior, okay? Because there's these intermediate length scales that you somehow need to capture. So this is an interesting story just from the perspective of single particles. Now, what would happen now if you have a porous electrode with lots of these particles undergoing phase separation? There's another sort of interesting story there. So imagine now here I'm going to show you a simulation here where you're going to see here, this is now a macroscopic porous electrode. We're kind of up at the engineering scale now. But in every one of the continuum volumes, which is represented by these little squares, you can imagine there's one or even a collection of particles, each of which undergoes the kind of dynamics that I just showed you. So it can undergo phase separation and that kind of behavior. And here's what's going to happen. You'll see in this movie a voltage step where you're suddenly extracting lithium. So the lithium content in the solid starts at 1, and this is the separator. You're going to see a sudden drop in lithium content there, which propagates. And as lithium is removed from the solid, it gets dumped into the electrolyte where it then diffuses away. And keep in mind, the traditional battery simulation models are all based on diffusion. Diffusion electrolyte, diffusion in the solid. Diffusion is a very smooth process. No noise, basically just everything very smooth. And I'll challenge you to see if maybe you could simulate this sort of thing with a diffusive model. Probably not, because you have all this sort of noisy stuff going on because these are phase transformations. So kind of the kind of non-intuitive thing is in a diffusive system, when you go slowly, the system becomes more homogeneous because concentration gradients are removed. Because in a diffusive system, in equilibrium, you have uniform concentration. But that's completely the wrong intuition when there's phase separation. When there's phase separation, equilibrium is constant chemical potential, which means you're either in one stable phase or the other. If the electrode is half full, it's half in one phase, half in the other phase. Very heterogeneous. So it requires kind of a big change in your way of thinking about these porous electrodes that could not be captured by previous models. And so here's an even more complex example of the kind of processes that go on in porous electrodes when you have phase separating materials. And this is again from another paper actually with William Chu's group, published now a couple years ago, where in fact this is the kind of visualization that the group was able to do. This is now not quite in operando during battery operation, but it's still in situ. So they basically discharged an actual porous electrode and then very quickly sucked out the electrolyte, took it to the X-rays, and started imaging it. Okay, so this almost like during battery operation. And this is a simulation, in fact, on the left by Ray Smith, who's also in the audience, my student from MIT, who's visiting this week. And you'll see here what we call the mosaic instability. So every one of these is a particle, and you can imagine every one of those is a simulation, like I showed you earlier, of a particle undergoing phase separation. But they're all interacting with each other now through the electrolyte. And you see across the electrode, you have this kind of complex behavior where there's a rate-dependent active population. So as you see here in the experimental data and in the simulations, you find that maybe only 10% of the particles are actually transforming. So again, very different from a diffusive model, which kind of shares the current across the whole electrode. It's really a big change of thinking, because also when people interpret experimental data, if they think, oh, I've got a certain current, amps per centimeter squared, let's say, and you just assume that that's uniformly shared by every surface in the material, right? But that's completely wrong when you have a phase separating system, because there's going to be a rate-dependent active population. So this is lithium iron phosphate, and we have worked on other materials. Another really important one is graphite. That is the standard anode material for lithium-ion batteries, as you may know. And it is also a phase-separating material, and it's actually a much more complicated phase-separating material. So when lithium goes into graphite, it basically starts to fill the spaces in between the graphene planes of the material. And if you look very carefully, there are a whole bunch of different stable phases. They're pretty close in voltage, so you don't typically worry about them. And in fact, traditional battery models have not worried about them. But I'll show you that I think it is important to worry about them. So in particular, if you look at voltage versus metallic lithium, so 0 is metallic lithium, as a function of filling fraction x, which is sort of how much lithium you've inserted, you again see these plateaus, but now it's more like a staircase. And from what I showed you before, you understand that every endpoint of a staircase is a stable phase. And what you're doing is when you go across a plateau, you're transforming one stable state into another by moving a phase boundary, either through a particle or across a collection of particles, like a mosaic. And so in this case, we've developed a model that actually has 3 stable states. So we don't actually worry about this one. We actually just worry about the state which is at filling 1, filling 1/2, which is every other layer, and filling 0. And we actually have sort of a 2-layer model that takes care of this. I won't go into the details, but we start out with a model that, this particular model is the blue curve. So it doesn't capture this stuff down here, but it does capture at least the 1/2 state and the 1 state. And here you're going to see a movie from some beautiful experiments done by Steve Harris at the time at General Motors on an unrolled graphite commercial electrode. And so basically the distances for transport are much longer than usual, but what's nice about that is you can actually see what's going on. Graphite has the property that as it intercalates lithium, each of these phases actually has a different optical color. So it's actually really nice for visualizing phase transformations. You don't need to use the fancy x-rays and things that we saw for lithium iron phosphate, where it was not so easy to see the different phases. And so the top is the movie, experiment, the bottom is the simulation. And we're actually just fitting one parameter here, which is the tortuosity of the electrode. So basically kind of a factor accounting for the sort of diffusion properties in the porous electrode. And the important thing is the model is able to predict kind of when the different phases pop off. The blue color was sort of the low density phase, the red was the 1/2, and the yellow was the full. And the dashed line, which you don't see in the movie, is our prediction of the electrolyte concentration that you can't see of lithium. Now, why does this matter? I guess I can try to sum that up here. So to be honest, a lot of this work was driven by scientific curiosity. But I'm a firm believer that when you discover new science, eventually it turns into useful knowledge and into useful engineering as well. And it doesn't always go the other way. Sometimes you just have to discover things and then you figure out what you're going to do with it. So we're slowly figuring out now some of the implications of this understanding. One of them is that you may wonder, like, how come we can't charge our batteries any faster? Especially for electric vehicles, we're pretty interested in charging our cars, faster than, a couple hours, right? We want to just get things recharged quickly, okay? And lithium-ion batteries have a decent cycle life. They're pretty good at recharging, but you can't recharge too fast. And one of the main reasons for that is that the nice reversible process is the insertion of lithium into graphite, okay? That's the reaction that you want at the anode. But the problem comes back to my voltage plot that I just showed you. This was the voltage of lithium and graphite versus lithium metal. So basically, if the voltage drops below 0 on this plot, and this is only 1/10 of a volt, then you start getting lithium becoming lithium metal rather than inserting reversibly as lithium intercalated into graphite. And once you have the metal, lots of bad things can happen. First of all, that's not the desired reaction, but also you can start to get metal growth, which I'll talk about in a minute, which can actually destabilize the system and even short circuit the system. Also, you have metal growth, which then when you dissolve and go the other direction, when you're discharging the battery, could break off a piece of lithium that becomes unconnected or disconnected electrically, so you get very fast capacity fade. So any way around it, you do not want lithium metal. So you have to avoid it. And here, by the way, from the same experiments of Harris, he's showing that if he cranks up the current in his simulations there, I mean his experiments, excuse me, notice this is the, where you see the yellow, which is the high density phase, it's basically right here. That's where you start to see the lithium metal plating occurring, which is the silver color here. And the main point of this slide and this work actually here is this comparison. So if we take a simulation where we use the traditional battery modeling approach, again, developed by John Newman and collaborators, we use the same electrolyte model they have, which is a very good model. And we do everything the same, except in one case, we assume the particles are solid solution, meaning they have the same diffusivity in the solid, the lithium does, but the particles are spheres, and there's diffusion in there, but there's no phase separation. Or we then switch to a situation where they are phase separating, so everything's otherwise the same. And then you try a simulation of charging the battery. And what's plotted here is the surface concentration of lithium in the solid. So basically, right on the surface of these particles, what is the concentration? Because then you know where you are on this plot to know what is your risk of lithium plating. Because if the concentration goes to 1, this falls off a cliff, and basically you could easily start getting metal plating. And what you find, again, as I told you before, diffusion is sort of the great equalizer. Everything's uniform when you have diffusion, okay? And so that's what happens here too, is that the surface concentration, even at this fairly high rate of like 6-minute charging, which is very fast, you're going to find that the surface concentration only goes to 60%, which you would say then you're over here, this is totally safe. But there's a fundamental difference, as I showed you before. When there's a phase separating model, that's not what happens. Things kind of pop one by one. You get this mosaic instability, just like you see in the movies here. And so the simulation with phase separation starts out uniform across the battery, and then you start to sort of nucleate the half-full phase, and then it becomes all half-full, and then you sort of nucleate the full state with concentration of 1, and then you have this whole region near the separator where it's under the largest stress electrochemically, which is basically full of lithium, and there's nowhere for lithium to go but to electroplating. Okay? So in fact, the two models predict radically different risk of lithium plating. And so if you want to predict and control whether or not lithium plating is occurring and hence enhance the recharging rate of your batteries, you have to understand and model this phenomenon correctly. So that is, takes us through the first topic. So I'd like to go through a couple other topics as time permits, relating to, again, mesoscale physics of battery materials. So I just mentioned lithium plating. So in the case of lithium-ion batteries, that's a bad thing. In fact, it's sometimes a really bad thing, as shown over here. But in other cases, we want it. So lithium metal is a great anode. In fact, it's kind of the ultimate anode because you can't really get much more lithium packed together. It has a very high energy density. So if you look at future batteries that are supposed to be for electric vehicles, notice they all have metal anodes. Okay, so down here are the intercalation type systems, or well, there's lithium ion in particular. But for future batteries, we're going to start using lithium metal. But it's not so easy, and there's a lot of challenges there. And for example, even in lithium air batteries where there's tremendous challenges on the air cathode, even if you solve all those, you've still got the lithium anode that you have to worry about, which has this potential problem with dendrites. This here is just an image just to point out that even in lithium-ion batteries, as I showed you on my last little discussion there, lithium plating is still bad. This is a funny story I can just mention as a side note. I was actually supposed to be on that plane, believe it or not. And even funnier, because it turned out well, it's not funny. It is, I can say it's funny, is that I was on my way to Korea to Samsung to give my first report for a grant on safety and lifetime of lithium-ion batteries. Believe it or not. And this was the slide I showed. I said I was supposed to come here on this airplane and there was a battery fire. So I'm not sure we've fully solved this, but at least we do know that dendrites have to be avoided, okay? And that problem is definitely something you can control for lithium-ion batteries as long as you don't go to too high rates and you have a good battery management system. But for lithium metal, it's just a fundamental problem because after all, you have a metal anode, so you have to understand it. So why do we get dendrites, which are basically these sort of finger-like patterns of metal, sort of fractal patterns you've maybe even seen in various situations like snowflakes or other kinds of patterns. So the way we understand them, the way that physicists actually spent a lot of time trying to figure out in the 1980s, is through processes such as diffusion limit aggregation. So this is a model where you have sort of imagine a sticky particle in the center, and you start releasing random walkers from far away, and when they get near the cluster, they stick, then the next one comes in and it sticks, and you get an unstable fractal growth right here, which is, by the way, colored by the time of arrival, so the red is the most recent. You see all the actions at the tips. The reason for that is when something sticks out, it's easier for it to get more diffusive flux, and so it sticks out more. And so it leads to an instability, and it leads to these fractal structures. It was recognized early on that dendritic growth of copper in copper sulfate solution is an excellent example of these DLA-type clusters, or at least it looks very similar. But here's a close-up of what lithium dendrites look like. And the word dendrite is often used in this field. And I'm going to argue to you that I think actually we need to refine our use of dendrite, because I'd rather use dendrite for this phenomenon and not just for any old rough growth. And that, in fact, this growth is very different and is, in fact, not really dendrites, actually. Just a brief point here, just to show the generality of these fractals. Actually, back in the day when I was doing more math, actually one of the things I worked on was fractal growth, and showed that basically all transport limit growth processes, at least in 2 dimensions, lead to these fractal type structures. In other words, they're all somehow equivalent to diffusion limit aggregation. So you kind of can't get around it. And that includes even if you add a fluid flow, even if you put the thing on a curved surface, like you're always getting this instability if you're transport limited. Okay? But are we transport limited in the case of lithium? Or are there more complicated things going on? So, so here's some really nice work that we just recently submitted, and this is really led by my postdoc Peng Bai. So he made a capillary cell experiment where he basically could visualize lithium growth in a liquid cell in a battery electrolyte and apply different currents and really see what happens to the morphology. And so here's an example of what Peng found, actually. So first, at this particular current density, which is not super high, you start to see this growth, which you can kind of see almost looks like it's growing from the roots. It's almost like kind of like a volcano bubbling over or something. And it's kind of still proceeding more or less like that for a certain period of time. And then all of a sudden, something happens. Okay? Now, in this field, people use the word dendrite to mean anything which is not flat. And now I'm arguing that that's, again, wrong, because you're, again, missing the mesoscale physics, which is the theme of this talk, is that not all non-flat things are the same. Okay, and as you just saw, there are at least 2 different transport mechanisms here, right? So what you saw at the beginning is what's sometimes called mossy lithium, and I'll explain to you in a minute what's actually going on there, and it's something different. But when you do reach transport limitation, what we show quantitatively in this paper, you get this very filamentary and fragmented fractal object, and that's the dendrite. That looks, in fact, very much like what I showed you on the previous slide. It's a highly branched structure, very open. You know, a fractal, by the way, is an object which lives in somehow a smaller dimension than the space. You know, so this is so fragmented that it somehow doesn't take up any space. That's what a fractal is. Okay. So this, and this obviously, notice how fast it was too. That's the dangerous thing. So when you're getting your short circuit, it's because this guy is exploding across the system. That's very bad. But if you avoid that, then you're back in this regime, which may or may not be bad. So if you look at, by the way, and when that happens, there's a voltage spike sort of that just precedes this. Because, and the reason is, I should mention, is sketched right here, is that when you're growing this kind of mossy lithium, the concentration profile is still able to, is such that basically diffusion is able to supply lithium ions to the growth. But the moment where the transition occurred, we show, is the so-called Sands time, which is when the concentration goes to 0, then you've hit diffusion limitation. So basically, either somehow there has to be faster transport, or the boundary has to move faster. And the only way for the boundary to move faster is to make these little filamentary structures that can kind of catch up to the ions. So it's kind of like the ions can't go this way any faster, so the metal goes this way faster. That's basically what happens at that point, at Sands time. And that's why you have the change in mechanism. So we looked at this quantitatively over a wide range of experimental conditions and showed that basically we have a simple formula to tell you as a function of the current density you want to apply and how much lithium you want to deposit. So how far you want to go in that movie, that's the capacity. Then there's basically a boundary you shouldn't cross. When you cross this boundary, you're going to start to see transport limitation, and you're going to be very likely to see these dangerous dendrites. And if you stay down here, you'll see mossy lithium. And we also can see then how to move this thing around. For example, changing the concentration of the electrolyte to a higher concentration could be helpful to move this boundary. We also did some experiments on the mossy lithium just to show that, as I'll show you in a minute, it's sort of like growing from the roots rather than the tips. And as a result, it's very easy to block as long as you have a hard structure with small enough pores. So people normally in the battery field use these soft polymer separators, and then the lithium more easily kind of bursts through. But what we did here, this is anodic aluminum oxide, which has really big pores. They're a few hundred nanometers, but they're totally open to electrolyte. And it turns out the mossy growth really can't penetrate it. But the dendrites can. So once you go over here, the dendrites just shoot right through. And so let me tell you a little bit about the mossy growth. So this here is actually work from my colleague Ju Lee at MIT and his postdoc Akihiro Kushima. And so this is a liquid cell high resolution TEM experiment, which is visualizing kind of in real time the growth of lithium on gold in this case. And this is metallic lithium. And so if you are at a relatively low rate or low overpotential, you find this kind of structure here. Notice it's very dense, and it looks kind of like the sketch up here in the upper left, which is kind of similar to what in physics we call the Eden model, which is where you're just simply growing in proportion to the surface reaction rate, but you're not limited by transport. That leads to sort of objects that are very dense, and in fact, they look an awful lot like these pictures here. But if you go to a little bit higher rate, and you're still not anywhere near transport limitations, so we don't have dendrites in the sense that I just showed you, there's also a change in mechanism here where you start to get what are called sometimes whiskers. Okay, and here they actually visualize the growth of a lithium whisker. Look closely here. So there it is. And see that little dot on there? It's clearly, it's growing from below. If you look closely, actually, it's not depositing at the tips. Interestingly, I don't know of any electrodeposition model that doesn't assume that the growth occurs at the tips. But the growth is actually occurring at the roots. Okay, so it's a completely different mechanism. And so it's kind of sketched here. What we believe is happening, and there's good quantitative evidence in these experiments, is that it's a reaction-limited process, but the essence of lithium growth, which is different from copper growth, is that there are two competing reactions. Because lithium is growing under conditions where the electrolyte is decomposing and forming the so-called SEI, or solid electrolyte interface. That's sort of the blue thing I'm sketching here on the outside of these lithium growths. And if you're at a high overpotential, that process happens so fast that kind of something starts growing, and then this film, passivating film grows on the top and shuts it down, and that builds up stresses until basically lithium is able to pour in underneath without being blocked by SEI, and it kind of pushes it forward from the root until enough SEI grows on the side to kind of shut that down. And there's sort of almost like this stick-slip motion. If you watch, it ends up forming this kind of like kinked whisker. And if you look closely, that's actually what's happening in mossy lithium. So a completely different mechanism than the process discovered long ago in physics having to do with transport limitation. Yes. So I could stop there, or I have a couple. How much time should I have?
Maybe just a few more minutes.
Okay, I could. Let me show two slides, if that's okay.
Perfect.
Two slides. Okay. So each of my topics is getting shorter because I knew I'd be running out of time. So here, just to kind of, again, continue with this theme of mesoscale physics and maybe even crazy ideas, this is some work that I'm doing that would appear to have nothing to do with batteries. In fact, I'm working on this initially for desalination. And this has to do with basically the transport of electrolytes through confined systems. In this case, this is you can imagine a microchannel, but it could also be a porous medium. This might be a pore in a porous medium. And then on the other end, we have a surface which is removing one of the ions. Imagine, for example, we're doing electrodeposition of lithium. We could also be passing the ions like through a membrane, kind of sketched here, like in a water desalination process. And the interesting phenomenon here is that if the sidewalls of this channel are charged so that you have double layers there that are present, that basically allows you to beat this limiting current phenomenon that I told you about earlier and sustain overlimiting current through what we call a deionization shock wave. So this is what's shown here. So here you have a neutral electrolyte of blue are negative and red are positive ions. And the walls are negatively charged. So there's lots of positive ions along the walls. And as you pass a current through the system, if it's a really high current, you start to get depletion of salt. But again, the theme is instead of being sort of diffusion, which is the usual assumption in these systems, you're able to get transport faster than diffusion. In this case, it's happening by electromigration of ions sort of going through the double layers to this surface. And this phenomenon actually was first discovered and described by some beautiful work in Juan Santiago's group, also with Ali Mani, who's now a professor in mechanical engineering as well, for the theory. And actually, Ali came to MIT as my postdoc, and we worked on this topic, and it's in fact been a major theme in my group. Just want to show you here at the bottom that this phenomenon has been thoroughly studied, and you can actually see it in experiments. Here, for example, are some fluorescent negatively charged ions, like the blue guys here. And you see this nice shock wave forming, and this is for transport of sodium chloride, or sorry, KCl, I think, to a Nafion membrane, so an ion-selective membrane in like a water desalination process. And so just very briefly, I think this opens up maybe some new kinds of electrochemical systems that we can think about that operate outside the normal operating regime, that can operate above the limiting current. So the main area I've been working on in this area is for water desalination, a process I call shock electrodialysis, where basically you're passing fluid through a charged porous medium, current goes in the other direction, you form this shock wave that I just showed you, and then you separate the fluid behind the shock wave, which is highly deionized, from the enriched fluid on the other side. And that's a water treatment process. But when it comes to electrodeposition, you can also say, any electrochemical process, how would it interact with these shock waves? What would happen if you drive these large currents? And so we've also shown that the shock, because it actually wants to be stable, it wants to be flat, it tends to stabilize metal growth behind it. So here we have two experiments using a porous separator material. And all we've done is functionalize the surface to be negatively charged or positively charged in this porous material. And this is, by the way, in the case of copper growth, I should mention. And we're able to grow copper in a stable fashion at very high currents by sort of stabilizing behind this shock wave. And so I leave the question, can this work for lithium metal? We've already seen lithium metal is a lot more complicated. So we'll see if that turns out to be true. And I think with that, I have one other little topic which I'll skip, and I'll just leave you with my conclusions. Thanks.
Thank you very much, Martin, for awesome electrochemistry and electrophysics. I actually was nostalgic a bit. I was a little kid at the time of the 1965 World's Fair. Some of you may remember the DuPont exhibit, Better Living Through Chemistry. So along the way, with all the technical details, without too much math, you actually created kind of a magic show, much as the DuPont exhibit did way back in 1965. So thank you for that.
Thank you.
Now we have a few minutes for questions. Anybody have a question? Students first, usually, to be very... here we go.
I think I might have missed it, but when you're talking about shock, is that just a sharp change in ion gradient?
Yes, so I'm sorry, the shock part went really fast. It was just to kind of get you thinking. If you're interested, please, contact me and we can talk about it in more detail. Oh, geez. Let's see what happened here. Okay, so somehow... Sorry. But yes, I just mean, so by shock, I mean sort of the mathematical definition of shock, which is that it's a sort of a propagating discontinuity. But it's a little deeper than that in the sense that if you look at the equations, as I didn't get a chance to emphasize here, normally in electrochemistry, if you open up a textbook, transport is diffusion. There's actually, or maybe convection, maybe there's some flow, but basically it's diffusion. And so dc dt equals, the second derivative there, so that's your diffusion equation. But in this system, because of those charged walls, you also have transport by electromigration, which means that the ions screening the surface charge are activated on by electric field, which is current divided by conductivity, which is varying. And this is a nonlinear advection term, which is well known lead to these kinds of shock phenomenon. So basically, mathematically, this equation is analogous to the equations of gas dynamics, shallow water waves, rivers, glaciers, traffic flow, which all lead to these sort of propagating shock waves. So that's the reason for it here. But this is kind of an electrochemical shock wave.
Other questions? Way back a couple of minutes. Is that Chris Jitsi?
Yeah, Mark.
All right.
Why is it growing from, why are these, what did you call them, whiskers, growing from the bottom electrode and not from, why is there a source from the substrate electrode? Do you know?
Sorry, you mean in these experiments here?
Yeah.
These ones here?
Yeah.
Well, so we do, you can verify that what is growing is lithium. So it's not coming from the substrate, it's coming from the solution. So you have a lithium battery electrolyte, lithium salt.
Wouldn't there be at least a as much chance of it getting to the tip as to the base?
Oh, it does. It does. So so the cartoon here kind of explains, if you analyze these movies very carefully, what you see is there is an initial tip growing phase. So what happens first is sort of the whole electrode is kind of dead, and then there's some kind of nucleation event happens. Maybe somewhere where the SCI layer, which is in fact on the original electrode, is sort of a little bit thinner or something like that, and it gets started. And then you sort of nucleate, and so you initially see the growth of a perfect hemisphere, actually. It's just nicely limited by growth on the surface, but it slows down. And interestingly, the growth rate slows down like 1 over square root of time, which seems like a diffusive process, but what we think it is, and quantitatively there's good support for that, is this square root of time of diffusion of solvent molecules through the SCI layer. So as this sort of film is growing, it keeps getting thicker, so it's passivating the surface, and eventually new solvent molecules can't get through. And so what happens is it starts growing like a hemisphere, but at some point the growth rate of the surface just gets way too slow, and you're demanding a higher current. And so it has to go somewhere, and it is a bit surprising. I wouldn't have predicted this, but this is what other groups have also observed. It somehow breaks away down here, and lithium starts kind of flooding in from below, and it just pushes this whole structure up, but only to a certain point. Presumably that's when SCI kind of grows on the sides and sort of shuts it down, until again somehow that stress builds up and maybe a little break opens here and a pathway comes in that sort of pushes it forward.
Does it happen similarly on other substrates, or is it only on gold?
Oh, it's not just on gold. It happens just even on lithium metal. Yeah, and in fact, and also the structures that grow in here, those whiskers are very similar to what you see in kind of like a normal lithium metal electrode, actually. Yeah. So, I mean, certainly the fact that it's on gold could influence the early moments of this particular experiment, but we think this is universal. And this is not the only group to have observed this root growth phenomenon. Some people have called this mossy lithium to be growing like a rising dough. So it's somehow like coming from below, and it's just like, I mean, it's very obvious. In fact, even in the capillary experiments I showed you, I think it's pretty obvious. If you look at them, it's not growing at the tips. I mean, maybe a little bit, but it's mainly somehow like just bubbling over like from below. So.
Lithium under potential deposits on gold, but it doesn't on some other substrates. And so you could imagine there's a reservoir of lithium that's everywhere under the SEI, and it's diffusive, so it can feed there, but that can't happen elsewhere.
So that's a good point, actually, and I agree with you that there could be some interesting interactions here with the gold substrate that might make this not so easy to observe exactly in this way on other systems. On the other hand, bulk mossy lithium appears to grow in a similar fashion from below. So we think that this general picture is probably relevant, but I think it is a very complex process. As I say, I think what's happening is pretty clear as we have at least 2 competing reactions when you're thinking about lithium metal growth, and you need to understand that interplay. And we certainly are not all the way there yet, but we're
just about out of time. Seeing no more questions. One more.
This is more an observational or phenomenological question, but in the 1D, capillary cell showing
Yes.
you're shooting
Yes.
dendrite growth on it.
right.
In the mossy phase, it really looks to me like there's another direction, like gravity going on in this. Is there some issue of the density that makes the thing curve? It really looks like a curve towards the bottom, like right now. You see
Well,
it
it does
down.
there, but that might just be because it randomly started there. So I agree that, well, there is some effect of gravity. I mean, definitely these things are heavier. And in fact, it's even been observed, actually, even in copper growth, that just the weight of copper ions in solution, if you change the concentration when you're depositing copper, it generates gravitational
Here's
convection.
another curving down.
Yeah, yeah.
phase. So I was just commenting observationally, you see that. And
Yeah,
so
that's a good
if you
point,
did this
actually.
experiment in a different orientation, like vertically.
Yeah,
or
well, we did
something,
try that. It doesn't
would be
change the
different.
phenomenon. No, it
You
doesn't.
can still
not
have
change
this
the phenomenon.
transition
Oh,
to
for
the
sure,
sudden
yeah.
rapid growth.
Yeah, definitely, yeah. And you can see here there's also less of that effect of gravity, I guess you could say. Something we didn't comment on here that actually does also occur is that you can see actually electroconvection as well, actually, because there's electroosmotic flow on the side of the capillary which circulates back, and that plays a role in the transport here as well when you get to high rates. Yes. But I agree, though. Gravity is playing some
One
role.
last question.
Just a quick one. This slide's going to be available online.
Slides online.
Yes, whether or not the video will be on there,
Yeah.
we're gonna try.
I tried to give Sunny my presentation, but it doesn't fit on her memory stick because there's all these movies. So basically, like the slides without the movies, we can definitely post, but then it's not nearly as interesting. So maybe we'll try to figure out some way to get these movies. Actually, this movie is part of a paper hasn't been published yet, actually, so that's going to have to wait a little bit. But otherwise, most of this work is published in
In
movies.
closing out here, on behalf of Sunny and myself, I'd like to thank Wayne Chu for having such a dynamite visitor and actually suggesting him as an energy seminar speaker. Thank you both.
Thank you.